Thank you, John, for this introduction. So I'm Andrey Malykhanov, and I'm from Amalgama consulting company. We do simulation-based consulting projects, and we also do some simulation models development for the major consulting companies. And my paper is devoted to distribution, network planning, and inventory optimization, which was supported by simulation in AnyLogic. I will not give you all the details of the project because of the time, but I will focus on modeling replenishment in supply chain because I believe it's the most challenging part of such models, and I will give you also some details about this data issue or big data issue we faced and how we overcame this issue. So I hope this works. Next. Okay. Why I have chosen this case study to present to you? First of all, it's a good chance to share our experience in real supply chain simulation modeling. Secondly, this case is a good example of combination of AnyLogic model and advanced data analysis technology. I will tell you about them later. And this is also a good example of real value brought to the client with simulation model. So, a couple of words about the background of the project. First of all, about our client, Diageo Russia. Is one of the Russian top 5 wholesale alcohol beverages distributors. As any type of this business, this is a low margin business with, which is very sensitive to logistic costs and customer service level. And our client came to us when he experienced the following issues. First of all, they experienced increase of logistic costs per unit delivered. So it's cost of goods sold, even with the growth of sales volume. So it was unusual, but it took place, and it was the first and major issue. And on top of that, they had plans of expansion to the eastern side of Russia, to Siberia and Far East. And moreover, they had plans of opening a new factory in Russia. That was kind of challenges for them. And what we asked to do is to show and prove the ways to decrease logistic costs and choose logistic network configuration for the expanded client network. So why did we use simulation? On this slide, you have so if you are an owner of a supply chain, the two indicators you would look at are basically service level, so how good you service your clients, and logistic costs, so how much does it cost you servicing your clients. And what basically controls you have is target stock level. You can set this or that stock level at your warehouses. You may also somehow influence forecasting accuracy by hiring more analysts, using more advanced technologies, and so on. You also can switch between different network configurations. So, if you are a supply chain owner, you want to know the correlations and interrelations between all those parameters. So, and the fact is that those interrelations are not so easy and not so straightforward. Actually, it's just a very, very high-level graph of interrelations. I will not stop at this in detail, but the other fact is that this takes place for each and every product. And the logistic resources are shared between the supply chains for each and every product. So you have shared warehouse capacities, shared transportation capacities, and everything influences everything. That is why we used simulation to capture all those dependencies. And what was the task that we solved? What was the exact task that we solved with the help of simulation? So the simulation task definition was for every logistic network configuration, we should determine how forecasting accuracy and target stock level influence logistic costs and service level. So we should capture those dependencies that from the previous slide. So that was our task. And let's take a look at the supply chain we have to model. So we modeled 3 existing and 1 prospective factories, 3 border crossing points, 3 existing and 5 prospective warehouses, 2 customs offices, and up to 300 demand points, which we grouped into 45 so-called service groups. And on top of that, so whenever you model supply chain, you also have to consider all many details, such as replenishment algorithm, order aggregation algorithm, delays at border crossing points. In this project, we have 280 product types and 6 types of warehouses. We also model demand and different sales forecasting accuracy for each and every product. We also had to consider transportation and load building algorithms. And what we did in this project is we implemented complete costing for each and every delivered product unit. So I will not dive into each point, but I will only highlight out of all this logic only replenishment algorithm to you. So let's take a look at what the replenishment algorithm is. It's just some segment of our supply chain, which is started at consolidation warehouse. Let's assume it has 5 days of lead time to central distribution center and another 5 days of lead time to regional distribution center. I don't know what typical lead times are in the US, but in Russia we have such numbers. So Russia is a big country with relatively slow transportation capacities. So if we look at the flow of demand, we will see that regional distribution center has its demand forecast. So does central distribution center. And the regional distribution center is 100% sourced from central distribution center, which is sourced from consolidation warehouse, but only at a rate of 60%, and it is sourced 40% from somewhere else. It is not important for our example. Regional distribution center has its own demand forecast, say for the next 20 days, for example. And when this demand forecast is basically the requirement, because the only requirement we have here is our planned demand. This requirement should be propagated to central distribution center, which is with the shift of 5 days. So here you can see the structure of demand plan for central distribution center. And likewise, this demand plan of central distribution center is propagated to consolidation warehouse, so at a rate of 60%. So to make the things simpler, if you plan to sell the bottle of whiskey at day 15 from now, you should have it at day 10 for now at central distribution center, and you should have 60% of the bottle at consolidation warehouse at day 5 from now. So that is how we model requirement distribution for each and every product, for each and every warehouse and distribution center in our simulation model. Let's go to the replenishment itself. So the replenishment is an algorithm which takes this requirement diagram or planned sales diagram. It also considers current stock, expected deliveries, some replenishment master data like lead time, minimum order size, proportion of sourcing, and generates the order. Basically not the order exactly, but the requirement for replenishment, but it's just not important. Okay. And what exactly this replenishment algorithm does? It builds the demand for the stock level forecast. The stock level forecast for each and every product for several days ahead. In our case, it's a replenishment planning horizon of 15 days. For example, if we plan to sell, if we plan to keep a stock of 15 days of demand, for example, in this example, it's 40 pieces of the product. That means that this number determines this corridor of stock, which is target stock level, lower threshold of stock level, and upper threshold of stock level. And this replenishment algorithm knows about the expected deliveries, and that's why it can estimate the forecast of stock level using also this rate of consumption. And what it does, it identifies the coverage gaps. So the time periods when our stock will be lower than our lower threshold, and it tries to do something with it. So in this example, it moved the order a couple of days earlier, and that is how it mitigated the first coverage gap. And as for the second coverage gap, it placed another order, a new order for this product. So what exactly it does, replenishment algorithm takes actions to prevent these coverage gaps for this replenishment planning horizon. All of this was implemented in our simulation model in each and every node of our supply chain for each and every product. So that is, I think that is it about the replenishment algorithm, and this was one of the issues that we have faced while in this project. And another issue started with model validation. So what we did to validate our model, we compared actual and modeled data for the year 2012. So we got some model data from our simulation model. We also got from the other side, we got some actual data by aggregation it from SAP ERP system of our client, and we started to compare it. And the results of the comparison shouldn't give us more than 5% of relative difference for every parameter for each and every month. What exactly we compared? Firstly, we compared demand volume, then we compared replenishment volume, stock value, and logistic costs. So the model considered validated only all the comparison is done and all the differences are explained. So, and what was the issue? So that is what we typically got when we try to compare modeled and actual data. On the top you see the stock level diagram day by day at Moscow warehouse. Actual data is shown in blue and model data is shown in red. We couldn't just take this diagram and go to the client, say, explain here and explain here, because otherwise we will never finish our consulting project and the client will not be satisfied. Let's take a closer look at what exactly we tried to do. Let's take some number, for example, from the end of the year. We took this number from the Excel report, which was produced by our simulation model in AnyLogic. So, and what we tried to do is, we tried to explain the difference. For example, we asked questions like, what is the structure of this number? What products have stock lower than actual here? Did we order less than it was required? Why did we order less than it was required if that took place? So what did we have to do? We have to relaunch the model, stop experiment at certain moment, look inside AnyLogic to try to understand what the model state was. And sometimes we even have to implement a new report in AnyLogic. So it would take us a lot of time to do this, and it was a real issue, a real problem. It has become a real problem for us. So what we proposed in this case is our new model structure. Here, the proposed structure you can see at the bottom. So what are the main differences? We included, we replaced report generation in Excel in AnyLogic with just logging. Logging is the writing of a very, very, very low-level events of simulation models, such as delivery arrival, or replenishment order placement, or daily stock report, product by product. We wrote all those logs into text files, which is much faster than using Excel, actually. And we feed it to the dedicated tool for data analysis. It is called Deductor. So it is, I'm not sure they have global coverage. I'm in the Deductor company. It is a Russian tool. It's rather widespread in Russia. But it is the tool that allows you to build data processing scenarios. As if in Excel, you should record all the sequence of commands of data transformation. For example, take this table, make a pivot table, sort here, calculate that, aggregate like this, and so on. And this is a data processing scenario. So we feed our logs into this Deductor tool, and we got the report themselves, which we aggregated all the reports with a macro in MS Excel to get the complete report with all the numbers, with all the with the capability to get down the structure of the numbers with all the charts and graphs. So the last thing the business consultant should do is to copy and paste it into the presentation for the upcoming meeting with client. And what other advantage that we have out of this structure is ability to compare several scenarios at once and to reflect the comparison results in the Excel report that was produced by our model. So, summary of advantages of this proposed new model structure. Experiment runtime decreased to 5 minutes. I will remind you that experiment might involve comparison of different scenarios. This is mainly due to we used text files instead of Excel files, and we also this is because we used the dedicated tool which performs the data aggregation faster. And what is more important, we're able to separate the effort or the work of AnyLogic modelers from the work of the business consultant. Anytime a business consultant needed new look at the data or new pivot table, new report, he might just go deeper into this deductor scenario and make a new report for his purposes. And this new model structure resulted in less time for model validation, more attention to business consulting, and more supply chain options that we considered. So that's to give you the video of the model. Yes, it's running. It's okay. So we pick up some scenarios. We launch the model. Actually, it should now show the animation. The animation was not widely used in the project, but anyway, it's there. So, okay, that's animation. You see the deliveries, the trucks coming between the warehouses and demand points and so on. But which is more important, we will now try to dive into one of the warehouses. I think it should happen so that's the general numbers that were collected during the simulation. It's all reflected in reports, so this was not widely used in the project. But if we dive into the warehouse, we will see stock diagram here, stock volume diagram. So it's in Russian. Okay, a stock diagram here, and some numbers that are simulated in the warehouses. And here you can see this replenishment diagram. I mean this for the product with an ID of 210. That's what we get. Okay, and here you can see this stock diagram and a list of expected deliveries and different data that were modeled in our simulation model. So let's get to some business results. It's just a very small example of what we got with our simulation model. So it's a comparison of two stock diagrams. You can see upper and lower stock thresholds here for the forecasting accuracy of 80% on the top and 40% on the bottom. You can see here that if we are accurate in forecasting our demand, we are more or less within this corridor, and we are not accurate if we are not accurate. If the accuracy is only 40%, we are sometimes out of stock, and sometimes we are very overstock. So, coming to the conclusions, that is the diagrams that we obtained from our simulation models. It correlates with our initial task. So here you can see the diagram of forecasting accuracy and so of service level depending on forecasting accuracy and target stock level. So target stock level is shown with different colors of plots, and forecasting accuracy is on x-axis, and service level is on y-axis. So we could obtain all those charts for each and every configuration, and not only for service level, but for logistic costs. And that is the result of the consolidation of our simulation results. We were able to prove to our client that its target state of supply chain model should be like this. It is called with 2B ball. The bubble size corresponds to target stock level. Bubble color is forecasting accuracy. And on x-axis, you can see here service level and logistic costs in relative currency unit. So I had to remove all the commercially sensitive information from here. That is a sample of a business result diagram that we provided to our client using not only the simulation results, but our business consulting experiments. So, and that is, I hope, the final slide. Business recommendations. So just a couple of examples of what business recommendations did we produce using our simulation model. For example, that's just real business recommendations taken from the real project, but I have removed all the commercially sensitive information and left only relative numbers. The payoff period of initiative for increased sales volume forecasting accuracy from 60 to 80% is less than 2 years. So they can do it. 20% increase of forecasting accuracy will allow to reduce target stock level by 40%, which will in turn reduce logistic costs per unit by 7%, even with their plans of sales growth. And opening regional warehouses will require unreasonably big stock to maintain target service level, even if they planned big sales growth volume in the regions outside Moscow. Thank you for your attention, and I will be more than happy to answer any questions, if any. Thank you.